All right, let's dive into something really cool today. Monte Carlo Reinforcement Learning. Now, that might sound like a mouthful, but the idea behind it is actually pretty amazing. It's all about how an AI can learn to win at something even when it starts out with absolutely no rulebook.
So let me ask you a question. Imagine you're dropped into a really complex board game or a maze, but nobody's given you the instructions. How on earth would you figure out the best way to win? Well, that exact problem, that's what Monte Carlo methods are built to solve for an AI.
I want you to think of our AI as a clueless explorer. Seriously, it's just been dropped into a new world. It has no map, no guide, no clue what the goal is. Its only option is to just start wandering around, trying things, and learning from what happens. It's learning in its purest, most basic form, just pure trial and error. Now, before a little explorer can really start its journey, it needs a few basic tools. And this toolkit is really the foundation of a whole field in AI called reinforcement learning. So let's quickly unpack the three key things our explorer has to work with.
First up, we've got the agent. In our story, the agent is our brave but clueless explorer. It's the AI itself, the part of the system that actually makes the decisions and takes the actions. It's the one doing the learning.
Next, there's the environment. This is just the world our explorer finds itself in. Could be a chessboard, a video game level, or even something as complex as the stock market. It's basically the stage where the agent's actions actually matter. And finally, the reward. This is the feedback the explorer gets from the environment. You can think of it as finding treasure, or scoring points, or maybe getting a penalty for a bad move. The explorer's whole goal is super simple. Figure out which actions lead to the most treasure, the maximum reward possible.
Okay, so our explorer has its toolkit, right? It's an agent in an environment looking for a reward. But what happens when that environment is a total mystery? When there's no rulebook that explains what happens if you turn left instead of right? Well, that's exactly where Monte Carlo methods come in. They are the special strategy the explorer uses to build its own map completely from scratch.
And this brings us to a really crucial distinction. On the one hand, you have what's called model-based learning. That's where the AI has the rulebook. It knows the odds and the outcomes before it even makes a move. But on the other hand, you have the world of Monte Carlo. It's model-free. Our explorer has absolutely zero prior knowledge. It can only learn by actually taking a step and seeing what happens next.
So how does our explorer actually learn anything? Well, with Monte Carlo, it doesn't really learn mid-journey. Instead, it has to have a complete experience, what we call an episode. This means it has to play an entire game from the very first move all the way to the final outcome before it can kind of sit back and think, okay, what did I learn from that whole experience?
Now, this might sound pretty complicated, but the core idea is surprisingly simple. Our explorer isn't doing some kind of mind-bending math. It's really just playing a game of averages. It tries something, it sees the result, and over many attempts, it just averages out those results to build its own internal map of what works and what definitely doesn't. The whole process is this simple but really powerful four-step loop. Okay, step 1. Our explorer plays a full game, start to finish. Step 2, it takes note of the final score, the total treasure it collected. Step 3, it then looks back at every single move it made during that game and updates the average value for each of those moves based on that final score. And step 4, it does this again and again, thousands, maybe even millions of times. Eventually, the moves that consistently lead to high scores just naturally rise to the top as the best strategy.
But this creates a classic problem, a real dilemma. Does our explorer stick to the path that it already knows leads to some treasure, that's called exploitation, or does it try a brand new, unexplored path that might lead to way more treasure, or, it could be a dead end? That's exploration. This trade-off is absolutely fundamental. If it only ever exploits, it might miss a giant jackpot just sitting around the corner. But if it only ever explores, it never actually cashes in on what it's already learned. Finding that perfect balance, That's the real secret sauce to learning.
So, like any strategy, our Explorer's Monte Carlo approach has some really clear advantages, but it also has some pretty big drawbacks. Let's take a look at the pros and cons of learning this way.
Okay, on the plus side, its foundation is incredibly simple. It's just averaging. That's easy to get your head around. It's also super versatile. Because it doesn't need a rule book, you can throw it at almost any kind of problem. And maybe the best part? It just works. If you give it enough games to play, it's proven to eventually figure out the best way to win.
But there's always a catch, isn't there? This method really only works for tasks that have a clear end, like a game of chess. It can also be a bit of a slow learner. Because it has to wait until the entire game is over to update what it knows, it can take a really long time to learn, especially in long games. And the results from one game can be wildly different from the next, which creates a lot of statistical noise in the data. So you might be thinking this clueless explorer analogy is a neat story, but where's this stuff actually used in the real world? Well, this exact strategy is behind some pretty incredible advances, everything from mastering complex board games to navigating the chaos of financial markets. It's a total powerhouse in game-playing AI. Think about training agents in backgammon or chess by simulating millions and millions of games. In robotics, it helps a robot learn how to move and interact with the world when the physics are just too complex to write down in a rulebook. And in finance, it's used to simulate thousands of possible market scenarios to figure out the best investment strategies. Now, our Explorer strategy isn't the only one out there. A close cousin is called Temporal Difference Learning, or TD for short, and this table really shows the key differences. As we know, Monte Carlo only updates its knowledge at the very end of an episode. TD, on the other hand, updates after every single step. It learns on the fly. This means MC can have high variance. Its results are noisy because one really lucky or unlucky game can skew the averages. TD has lower variance since it smooths things out as it goes. But on the flip side, TD has a higher bias because it's making estimates based on other incomplete estimates, while MC has low bias because it always uses the true final score.
If you're going to remember one thing, it's this. Monte Carlo is the patient learner. It waits until the whole game is over to see the final score before it makes any judgments. Temporal difference is the impatient learner. It looks at what happened after every single move and updates its strategy right away.
And that really brings us to our final thought. This ability to learn from pure experience without anyone handing you a rulebook is incredibly powerful. We've seen it master games and optimize financial models. So the real question is, as this technology gets better and faster, what's the next big, complex, real-world challenge it's going to solve? Thanks for tuning in.